Today, we're going to dive into what might become your new favorite geospatial tool, SedonaDB. The geospatial stack is changing very quickly, but unfortunately, a lot of the tools we use weren't built with spatial as a core feature in mind. SedonaDB is focused on spatial operation. It's a single node engine that can run right on your computer. You can use both Python and SQL, and it's built to handle spatial data efficiently. Today, we'll talk a little bit more about what it is and do a quick demo to show you some of the features and functionality. So with that, let's dive in. So let's take a look at the SedonaDB homepage and break down what this means. SedonaDB is an open source, single node analytical database engine with geospatial as a first class citizen. It aims to deliver the fastest spatial analytics query speed and the most comprehensive function coverage available. So if we break that apart, it basically means that it runs on your computer or any other virtual machine and that you can install it on. Think of something like a Jupyter Notebook service or anything like that. Basically, it's fast and it can run on your computer without a distributed backend like Spark or any other distributed system. Now, analytical engine basically means that it runs analytical queries where you can ask questions like how many of these things fall within a different thing or a spatial join, maybe do some lightweight spatial processing, or do some aggregation and things like that. It is not a fully featured database where you can do inserts, updates, and deletes. It works on data files that you have or can get access to, either locally or via the web, and allows you to ask these analytical questions. Now, geospatial as a first-class citizen effectively means it really is focused on working with and processing spatial data efficiently. As you can see here, it's really good for these small to medium data sets, and that can mean a couple of different things depending on what you mean by data set size, but effectively it can handle some pretty large data sets and read data directly over the cloud from services like S3 and public buckets or private buckets with proper authentication. To boil all that down, it's a really easy way to get started with cloud-native geospatial data and allows you to do that very quickly, faster than other engines that are out there. Now, I've talked a lot about different engines in the past, and the beauty of some of these different engines that allow you to leave data on some server somewhere or a cloud bucket, so you don't actually have to download anything. You can just read it over the web. And this does specifically that, but it's focused on spatial operations. Now, it's also very easy to use. You can basically go ahead, install it with pip and integrate it with Python. You connect your database as you can see here, and then you can read in different files such as Parquet, or if you have different file types, you can pull that into a GeoPandas data frame and then read that into a view in SedonaDB as a registered table or view on that database. Now, again, this is all in memory. You can't save the database out or anything like that, and it doesn't handle inserts and updates or deletes the way PostGIS does. Now, there's some really great guides on the documentation. You can see how to get started here, how to create different data frames, reading Parquet data, registering it as a view, and then effectively that allows you to write SQL queries against that data set in memory. Again, as you can see here, this is coming directly over the web, so it's reading data that's remotely somewhere else and not downloading that to your computer. For large data sets, this is really advantageous. Now, you can also read in different file types like GeoJSON, shapefiles with GeoPandas, and then pull those into a SedonaDB data frame, as you can see here, and then start writing queries against that. This is probably one of the easiest ways to get started using Overture Maps data, specifically when you're working with the geometry data sets. So you can read that over the web here, see the data, and do some basic queries. It's also very efficient for handling projection systems, so translating between different projections handles that really efficiently, and we'll actually take a look at some examples of that. So it becomes less of a headache compared to other analytical systems where maybe there's some few other steps or maybe there's lacking some of that support in different systems. Now, once you've processed some data, you probably want to be able to save it. You can actually read and write out different Parquet files, as you can see here, and you can do a lot of different things. And you can see that there's full support for spatial SQL within this, and you can read different data and query it this way. So there's a full list of documentation here, but again, this promises to be one of the fastest and most efficient services for processing spatial data. And they've actually published Spatial Bench, which is a benchmark that anyone can use and run to compare the performance across different systems. So you can take a look at that here, but we can actually see some of the results on single node services. This looks at things like GeoPandas and DuckDB, and you can see in this chart here that overall SedonaDB does quite well across all these different queries. What I really like about this is it actually takes a lot of common spatial operations that are more complex than just a simple spatial join, and you can kind of see what those different query types are here. So there's complex spatial joins, nearest neighbor joins, a bunch of different types of queries that are actually run and performed. We're going to take a look at in the demonstration here to see how those different queries query types break down, some more advanced spatial processing, which is a very common use case, but can be incredibly slow on other systems. Now, I put together a blog post, which you can actually check out here, and it does a full deep dive across things like SedonaDB, DuckDB, and PostGIS, which are 3 common engines that I've used in the past. There's also, GeoPandas, which you could compare as well, but these are SQL systems, so it made sense to compare some apples to apples here. Now, it doesn't talk about just the speed of all these different things, but also the process to get that data in, what these things are really good for, and when you should use them, and how you can use them in unison. Now, I'm a really big proponent of using the right tool at the right time. So this can kind of give you a sense of how you can use SedonaDB alongside of PostGIS and alongside DuckDB. Each of these tools have very different strengths and weaknesses, so it's important to understand how they fit together. Now, there's some data here that you can go ahead and download. I wanted to kind of include it to be, like regular geospatial data, so it's not all cloud native data. It's actually data from my book on spatial SQL, so it pulls in some common query patterns that I use in that book, or more advanced spatial processing queries that I like to run to kind of test these different systems out. So you can download that Google Drive folder here, and then all the code is here on this GitHub, and you can see some of the different steps to run that here. So this talks about how you set up a PostGIS database to do these different things, and then some of the queries and how those queries look compared in these different systems. So we can go ahead and get started. All you have to do is basically install Apache Sedona, as you can see here. This notebook will compare the queries across SedonaDB and DuckDB, and then you would have to set up your own PostGIS instance to do that. So let's go ahead and start our SedonaDB instance here. All I have to do is import sedona.db after I've set up the install, and then you can connect that here. And you can see I have some different files here. This is just some open data, and you can see how you can read that in over the web. It allows you to skip the AWS signature. I can go ahead and read that in, and now I've read that remote file here, which is just a really quick example to show you how to do that. This is just some data from Source Cooperative. Now, as you can see here, I can write a simple query against that. And again, all this data is sitting somewhere else. It looks like it's in the US West 2 region. I can query that, and I get all my data here directly over the web, which is amazing. So that speaks to the cloud native compatibility to that. Now, for the data, if you're following along in the tutorial, I've pulled in some different data from the New York Open Data Portal. And since it is in GeoJSON and I think shapefile format and things like that, I actually have to use GeoPandas to read that in. So what I'll do is I'll create a GeoPandas data frame. This is all the building footprints in New York City. So that's what it's creating here as this geodata frame. And this will take a minute to load that into memory. But then, as you can see here, I'm going to create basically a database version of that. I'm using SedonaDB to create the data frame, create the SedonaDB data frame from the GeoPandas data frame, as you can see here. And then I can read that out. So now I've established my data frame, and once that's set up in SedonaDB, I can pull a few different operations. This one will allow me to show the number of rows, basically the first 3 rows, very similar to a GeoPandas operation. You can see here's the data that's in that. If I wanted to expand that, I can basically set that up so it can show all the different data. So I can set that up to show all of it, and you can actually print out the schema of the file as well. So you can see here's all the different columns in that data. I'm going to pull in a few different data sets. These are fire hydrants across New York City, as well as neighborhoods or neighborhood boundaries, and then the census block groups across the entirety of New York State. And then it has some different data in there from income, as well as population and median age. Now, basically, to set these up so I can query them, I have to establish them as a view in the database. So as you can see here, I'm basically taking those DB objects, which store the data, and turning them into a view with the same name. So that's all that's happening here. Now I can actually start to query these. And I'm going to do a few different queries just to sort of demonstrate what this looks like. So in this one, I'm basically doing a very basic spatial join. I'm counting the number of buildings in each neighborhood based on st-intersect. And you can see what I'm doing here. This just sets up the query. And then down here, I'm actually going to call execute, which will execute the query. So you can see here, it'll tell me how much time that took. And that took 0.3 seconds to do that entire join. Now we can basically take a look at the data here. So we can do something like count, and you can see here that there's 263 polygons here. We can actually see for the number of buildings, some more data, it's about 1.2 million buildings. So this isn't, massive data, but it's not small either. And you can see even with that scale, it runs incredibly quickly from that speed. And what I can also do is take a look at what is in the data here. You can see here's the number of buildings in Fresh Meadows, Morris Park, University Heights, all the different neighborhoods here that have been listed. So That gives us that data back. You can modify that query to include the geometry and then write that out as a Parquet file, as I mentioned earlier. So let's go through a few other queries, take a look and kind of compare the performance against them. And then we'll jump into, okay, now that I've ran these queries, what can I actually do with this data once it's done? So these are some of the more advanced spatial queries I like to run and kind of compare and test. If you're generating features for spatial analytics or even machine learning workflows, this is going to be a really important step. So this one is actually looking at the number of buildings within 200 meters of a fire hydrant, right? What I can do here is count the building count and use SQL to do that. And then the unit ID is the actual fire hydrant unique identifier that I'm looking for. Now what I'm doing is I'm going to use std within, or distance within, and you can see here I can actually perform this as a transformation. Now there are other functions you can use as spheroids, so you don't have to move these back and forth. This data comes in two different projections. One is I believe the state planar for New York State and Long Island, so it's actually measured in feet, and the other was in 4326, which is measured in decimal degrees. So in this step I want to standardize both of these, and it's incredibly efficient to do that. If you did st transform in other databases, it might take a little bit longer. So I've seen that take an extra step, and sometimes there's things you have to do to modify the actual base file. Here, you can just do it automatically and inline. So let's go ahead and take a look at that. And then what I can do here is run that query. You can see that took 1.8 seconds. Again, for the size of this data, let's just take a look at that here. And buildings, I think we already know that's like 1.2 million. And there's like 109,000 different fire hydrants. But let's take a look at that. You can see here, to show the data, that it's relatively evenly balanced. There's give or take 150 to 200 buildings within 200 meters of every fire hydrant. I mean, this might vary depending on where you are in the city, but of course you could order this. You could do some, different things to investigate this a little bit further, but basically still incredibly fast for that volume of data. Now we also want to look at area weighted interpolation, right? This is one of my favorite queries to write. So if you take a look at this image here, it might show up a little bit grainy on your screen, but basically these are census tracts or block groups or any census measurement. These are generally polygons, and it says maybe for each of these there's 100 people that live in each of these tracts. And what I want to investigate is how many people live in this buffer area. So if we imagine that, in each of these, if we just took the intersection, we would say, 400 people live there. But obviously the majority of those people fall outside of this. So maybe for each of these two areas, there's 50 people that live in the intersecting area. And we can calculate that by calculating this area overlap of this circle against this polygon. And we can basically take the percentage and approximate how many people are there. So let's say in this area here, in this area, there's 50, so that'd be 100. In this area, there's 25 and 25. We can approximate that and say that that's 150 people that live in this cell, which is a big difference from that 400. So this is really a simple way to do this. There's more advanced methods that, are beyond the scope of this video, but for a quick calculation, you can do this really efficiently. Now to do that, we have this kind of funky function here. I'm going to multiply the population in that specific area. And what I'm going to do is basically on this top level, take the intersection, which is the area, basically calculating this area between these two, the intersected or clipped area. And basically I'm creating a buffer around my building of 800 meters. That's one. And then the census block group polygon here. So let's say that is about 50 meters. And then the area of the entire census block group, and that, for argument's sake, let's say that's 100 square meters. So basically I'd end up with 0.5 when I've run this calculation, the area of that. And once I've calculated that decimal, I can get 0.5 back. I'll multiply that by the population. Let's say the population there is 100 times 0.5, I'd get 50 back. And then what I'm doing is I'm doing that for each intersection. I'm going to group that by the bin or the building ID, and then I'm going to calculate the sum. So the sum of all of them based on the grouping of the building ID. So for each buffer, there might be 5 to 10 to 2 intersecting polygons. I'm going to sum all of those up and calculate it that way. So it's a pretty complex kind of computation when you think about it. And as you can see here, I'm doing this for every building in the city, all 1.2 million.
I'm doing the projection on the fly, I'm calculating the overlap, I'm doing the clipping, I'm doing the transformation. All these steps here are taking place, and it only took 8 seconds here. And then we can see here, if we go to just show what this data looks like, you can see that, it tells us the approximate population. You could do the same type of calculation for things like median age, median income, all this different stuff. So we can see here that for each building, they have, anywhere from 1,500 or so up to the most is about 37 or 3,800 people living in those 800 square meters around that building. So it's a really great way to get that estimate of population. Now, the final one is a KNN join. This is another complicated one where it says, I want to figure out the 5 nearest things to that. And this is, one of the more complex queries to write. If you look at how you do this in even DuckDB or in PostGIS, you have to do this kind of complicated cross-lateral or cross-join lateral. So it's this kind of very strange join that isn't used very often. It's cool to know, but it's a little bit unnecessary and sort of complex, right? When we look at SedonaDB, and we look at the SQL here, it has STKNN, which is basically wrap that into one single function. And what's nice is you can use the spheroid if your projection's in 4, 3, 26 or decimal degrees. I don't have to transform that back and forth. It gives you the number, and you can basically kind of, search all these different values here. So what I'm going to do is get the building ID, the hydrant ID, the distance between those, and I'm going to join those two based on the 5 nearest, right? So for each building, I should be getting back 5 fire hydrants and the distance to those fire hydrants. So let's go ahead and take a look at that. And this is one that's incredibly fast to run. So, and we can see our results here. So let's pull the top 15, because remember, this would be for 3 buildings. And then you can see here, so this is building ID. You can see it's repeated 5 times. You can see here, here's the different ones, and here's how far they are from each of those. So I do need to transform these to get distance in meters, which is what I want. So let's go ahead and make sure I'm doing that correctly. And then we can just rerun this. And here you can see that now it's in, here's 34 meters, 80 meters, so on and so forth, up to 144. So that's basically it. And you can see even now that I added this transformation step, it's still very fast. It's easy to calculate all these different things, make it very speedy. Now, of course, I wanted to kind of compare both the speed results of this, but also the complexity of the code you have to write, as well as the steps to get there. So for DuckDB and SedonaDB, you can basically read the files as they are. If you wanted to go through this notebook and do the same comparable functions and data sets from DuckDB, you can do that here. So you can kind of compare the runtimes. For Postgres, of course, you have to move that data into memory. And in this step, I basically did all the things to kind of optimize this as much as possible. So I'm loading the data in, as you can see here. I set up, they have instructions to set up your own PostGIS database with Docker. So you can build that, connect that to, QGIS if you want to. And basically, what you can do here is you have to, add the table, update the geometry, create 2 different geometry columns for 4326 and 3857, and then create an index on that. But now you can kind of compare the speed. You can see here, SedonaDB did this in, 0.24 seconds. DuckDB took 43 seconds, and PostGIS took 6 seconds for the basic spatial join. For the distance with an aggregation, SedonaDB took 1.3 seconds. DuckDB was 41 seconds. PostGIS was 21 seconds. Now for area weight interpolation, SedonaDB was 6 seconds, PostGIS was 28.9 seconds, and DuckDB was 97 seconds. And then for the final one, this is the KNN join. DuckDB threw a memory error. SedonaDB took 1.8 seconds, and PostGIS took 83 seconds. So it's not the most important determining factor. There's also the ability to get up and running very quickly. DuckDB is really important for that. That's why I really like it. It's just fast and easy to install. But SedonaDB provides that, plus the experience to work with these queries very quickly and iterate and develop. You're not waiting around for long periods of time for these things to run. You can also have the CRS support for the reprojection of data and all these different things. So it's very fast to move that in. And plus it fits in with a modern Python ecosystem. You can create maps with things like Lawnboard if you want to build them with Kepler-GL. And most importantly, if you need to write data out, you can actually write data as Parquet files and basically save your data as that. So you can see here, you can set this up to write to Parquet, set up an output path, and then write those results to Parquet. You can partition it. It's a really easy way to start to create
data or analytical results, save that in GeoParquet format, and get ready to go. So with that kind of covers this tutorial for SedonaDB. I'll save the links for the blog post, which has the code and the data so you can run this yourself, as well as the documentation links where you get started. Love to hear what you are going to build with SedonaDB, how you might be using it, and if you have any questions, obviously drop those in the comments below.